Hello student, hi, how are you? Good evening. So today we are going to see intrinsic carrier concentration. Okay, so intrinsic carrier concentration, and in last class that we have seen the thermal equilibrium concentration of electron and hole in semiconductor. Okay, so today we are going to see intrinsic carrier concentration of electron and hole. This is what intrinsic intrinsic carrier intrinsic carrier concentration intrinsic carrier concentration of intrinsic carrier concentration. Okay, intrinsic carrier concentration, today we are going to see this in semiconductor. Okay, so in intrinsic semiconductor the concentration of what, if you see in 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 intrinsic in intrinsic semiconductor in intrinsic semiconductor in intrinsic semiconductor material in intrinsic semiconductor material concentration concentration of electron and hole concentration of electron and hole are equal. Okay, so that is what n is equal to, that is like n naught is equal to p naught is equal to what, ni is equal to ni. This is intrinsic carrier concentration of electron and hole are equal. This means that the number of electron in conduction band is equal to the number of electron in valence band. Okay, so that is for intrinsic semiconductor material. These are intrinsic carrier concentration. Okay, so these are the intrinsic carrier concentration of electron and intrinsic carrier concentration of hole in intrinsic semiconductor material. Okay, intrinsic semiconductor material. Now we will compare this with the equation that we have seen in the last class. That in last class, the equation that we have seen for thermal equilibrium concentration of electron and hole in where in semiconductor material. Okay, at what thermal equilibrium concentration, that is what that we have seen what thermal equilibrium concentration of electron and hole, and we have derived the equation for electron and hole, that is what n naught is equal to nc, n naught is equal to nc into e to the power minus ec minus ef by kt. Okay, kt, this is thermal equilibrium concentration of electron in conduction band. Yes, in conduction band, and similarly we are equating this n naught is equal to ni, okay, so now similarly for hole, p naught is equal to what, p naught is equal to nv e to the power minus ef minus ec by kt, is equal to what, is equal to ni. Okay, so is equal to ni. So these are both equal. Okay, so you can say like this, pi. So both are equal concentration. Okay, concentration of electron is equal to concentration of hole, and both we can denote both electron concentration and hole concentration by ni. These are what intrinsic carrier concentration in semiconductor. In intrinsic carrier concentration in semiconductor for both electron and hole. Okay, which are equal. Okay, which are equal. Now see here, if you see here, this is what ni. Okay, so these are two equations, equation 1, equation 2, equation 2 for equation 1, equation 2 for both intrinsic carrier concentration. Okay, so intrinsic carrier concentration. Now let us take what, product. Okay, we are taking the product of these two equations. Then what we will get by taking the product for these two equations on both sides, if you will see, we will get eta I square is equal to nc nv into e to the power minus ec minus ef by kt into e to the power minus ef minus ev by kt. Okay, so this is what product, we are taking product for both this equation. Okay, product on both side, we will get eta e square is equal to nc nv e to the power minus ec minus ef by kt into e to the power minus ef minus ev by kt. Now just we will express it like nc nv, just open this nv e to the power, just simplify this. What we will get after simplifying, this is minus ec, this is plus ef, because base are equal. Okay, when base are equal, then power will get added. Okay, power will get added, so that is what minus ef plus ev divided by kt ef get cancelled. Okay, so now we are left with what, ni square is equal to nc nv into e to the power what, if you see, minus ec minus ev minus ev by kt. Yes, ec minus ev by kt. And if you see this, ec minus ev is nothing but what, eg, energy band gap, is equal to what, ec minus ev. Yes, now we can write ni square is equal to nc nv into e to the power minus eg by kt. Okay, so this is my intrinsic carrier concentration. Yes, intrinsic carrier concentration. If you see nc and nv, what is this nc and nv? If you see this nc and nv is nothing but, if you see nc is the density of state function in conduction band, which is nothing but 2 into 2 pi m n star kt mn star kt by h square to the power 3 by 2. Yes, and nv is nothing but 2 into 2 pi mp star kt divided by h square to the power 3 by 2. Yes, to the power 3 by 2. Now if you will see this, just take this all constant except temperature, so we will find this ni square is equal to a strict, this is star, okay, into t to the power 3 by 2 e to the power minus eg by kt. Okay, so this is what this a strict is nothing but, if we see a star value, so this is just you can say here mn star, you can take here this is strict, this is what t. Okay, nc nv t square t cube. Yes, t cube, so this is what t cube. Okay, so this is a star t cube, and this a star value is nothing but, if you see, this is nothing but a star value nc nv, this is nothing but 4 into 2 pi mn star mp star. Okay, so just you see remaining, whatever remaining is there, this is nothing but a star. Okay, a star value, whatever remaining is there. Okay, so you can say like this, a star is equal to 4 into 2 pi mn star mp star mp star k divided by what, h square whole square. Okay, so these are 3 by 2 means cube. Okay, so this is my A star value, and this is what eta ni square is equal to A star. Means what we want exactly what this eta square is proportional to TQ. This means what? This means the intrinsic carrier concentration is a strong function of temperature. It is a strong function of temperature. Okay, so this is strong function of temperature, and we can say that for a given semiconductor, for for given for given semiconductor given semiconductor material given semiconductor material at constant temperature at constant temperature for given semiconductor material at constant temperature, intrinsic carrier concentration is what? Constant. Intrinsic carrier concentration Ni is constant. Ni is constant and is independent independent on Fermi energy. Fermi energy. Fermi energy, as we have seen here, Fermi energy has got cancelled. Okay, so therefore we can conclude that what intrinsic carrier concentration is a function of temperature. Yes, is a function of temperature, is a function of energy band gap. Okay, and is independent on what? Is independent on Fermi energy level. Okay, so for a given semiconductor, if the semiconductor is given, okay, at a constant temperature, then here intrinsic carrier concentration is constant. Intrinsic carrier concentration is constant and is independent on Fermi energy. Okay, so if we see here, for intrinsic carrier concentration for silicon at room temperature, intrinsic carrier concentration for silicon intrinsic carrier concentration for silicon at room temperature is how much? Ni is equal to 1.5 into 10 to the power 10 per cube centimeter. Okay, so this is what? Intrinsic carrier concentration for what? For silicon. So similarly, if you want to see, for this is for silicon. Okay, so similarly intrinsic carrier concentration for germanium is 2.5, approximately 2.5 into 10 to the power 13 per cube centimeter. Similarly, for intrinsic carrier concentration for gallium arsenide is 1.8 into 10 to the power 6 per cube centimeter. Okay, so these are the intrinsic carrier concentration for silicon, germanium and gallium arsenide. Okay, so now if we see here, if we see from this point, this Nv and Nc and Nv, which is nothing but density of state function in conduction band and in valence band. Okay, if you see this, if you observe carefully, this is what? These are the function of effective mass. Okay, these are proportional to what? These are proportional to effective mass of electron and hole. And this effective mass is what? This effective mass is nothing but, this effective mass is what? It's not a general parameter. It's a just experimentally determined parameter. Okay, so this effective mass is actually a experimentally determined parameter. It's not a general parameter, and it is what? It can be determined at low temperature. Okay, it can be determined at low temperature, and this effective mass here, this effective mass is what? It is a measure of what? It is a measure of how well the particle move within the crystal. Okay, how well the particle move in the crystal. This is what? This we can say by with the help of this effective mass. Okay, this effective mass, and slightly this effective mass is also a function of temperature. Okay, function of temperature. So this is about effective mass. What is effective mass? Effective mass is nothing but, it's an experimentally determined parameter. It's not a general parameter, and it is determined, basically it is determined at low temperature, and it is a measure of what? It is a measure of how well the particle move how well the particle move within the crystal. Okay, that we can get with the help of this effective mass. Okay, so now we are going to see the intrinsic Fermi level. Okay, intrinsic Fermi energy level. Okay, so that we have seen what intrinsic carrier concentration. Okay, intrinsic carrier concentration that we have derived. Okay, it is a function of what? Energy band gap, temperature. Okay, it is independent on what? Fermi energy level. So therefore at any constant temperature eta is constant. This Ni is constant means intrinsic carrier concentration is constant for a given temperature. Okay, and is independent on what? Fermi energy level. Okay, so now let's go for intrinsic Fermi energy, intrinsic Fermi level. Okay, we will see intrinsic Fermi level. So this is about intrinsic carrier concentration. Now let us see intrinsic Fermi level. Intrinsic Fermi level, intrinsic Fermi level. Intrinsic Fermi level, if you see here, intrinsic Fermi level, as we have seen that actually the Fermi level is lies where? What is Fermi level? That we know very well. Fermi level is what? Fermi level is the level, is the Fermi level is the energy level below which all. Okay, so Fermi energy level is what? Actually it is a intrinsic, it is what? It is a imaginary level. Okay, hypothetical level. It is imaginary level, hypothetical level, below which all the energy state are filled, above which all the energy state are empty. Okay, that we know about this Fermi and Fermi level. Okay, Fermi level. So now here we will see the intrinsic Fermi level. Actually, as we see the Fermi level that actually lies near what? Near the forbidden energy band gap. Okay, it lies near the forbidden energy band gap. If we see in case of what? As we know, in case of intrinsic semiconductor material, the concentration of electron and hole are equal. Okay, hole are equal. Okay, so then with the help of that comparison, we can determine this intrinsic Fermi energy level. Okay, so now see, as we know very well, what intrinsic carrier concentration of electrons and hole, that is equal for both. Okay, so that is what? Ni is equal to what? Ni is equal to Nc. Ni is equal to Nc into e to the power minus Ec minus Ef. Now we are writing it as EFI. It is intrinsic Fermi energy level. Ec minus EFI by kT is equal to Nc is equal to what? Nv. Nv is equal to minus EFI minus EV by kT. Yes, which is nothing but Ni. Okay, Ni is equal to Nv. That is both are equal. Okay, Pi. So these are what? These are intrinsic carrier concentration where in intrinsic semiconductor material. Okay, intrinsic semiconductor material. Now we are trying to what? We are trying to calculate this. We are trying to find the position. Okay, so this is what intrinsic Fermi level, or we can say the position. Okay, position of intrinsic position of intrinsic Fermi level. Position of intrinsic Fermi level. Okay, so position of intrinsic Fermi level, if you see here, Ni is equal to what? Ni is equal to Pi is equal to this. Okay, so now we are equating both these equations. Okay, let us now equate both this side. Okay, so this is what? Intrinsic carrier concentration, that we know very well. Okay, so that we have seen in last case. Okay, in case of intrinsic carrier concentration. Now see here, now let us compare it both side. Nc. Okay, so Nc into e to the power minus Ec minus EFI by kT is equal to what? Is equal to Nc is equal to Nv. What? Nv into e to the power minus EFI minus EV by kT. Okay, by kt. Now we are equating this. Okay, so let us take this and see this side. Okay, so we will get e to the power minus ec minus efi, ec minus ef by efi by kt is equal to nv by nc, nv by nc. Okay, e to the power minus efi minus ev by kt by kt. Okay, so now see here, just take logarithmic. Okay, take the log on both sides. Okay, so now take natural log on both sides. When we take the natural log on both sides, what we will get? ln e to the power minus ec minus ef by kt is equal to ln nv by nc, nv by nc. Okay, so this is my ln nv by nc into e to the power minus efi minus ev by kt. Okay, so now if we see this here, log e to the power x, as we know very well here as we know very well, ln e to the power x is equal to what? X. Okay, ln e to the power x is equal to x. Similarly here, ln e to the power ec minus ef by kt is nothing but we are left with what? Minus ec minus ef by kt is equal to what? ln. Apply here product rule. This is what? A b. So log a into b is what? ln a into b is what? ln a plus ln b. So just apply this. ln a is nb by nc plus ln, similarly ln e to the power efi minus ev by kt is what? If you see this, ln e to the power minus efi minus ev by kt. Okay, so now see here, minus, just draw this line here. So this is what? Minus ec minus efi by kt is equal to ln nv by nc. Okay, nv by nc plus ln, similarly same, ln e to the power x. ln e to the power x is what? X. So x here is what? efi. This is what? Minus efi minus ev by kt. So now see, so let us take this side. Okay, so when this will come this side, it become positive. So this is nothing but efi minus ev by kt minus, this is my minus. Okay, so minus ec minus efi by kt is equal to what? ln nv by nc. So let us see here, efi minus ev minus ec plus efi by kt is equal to what? ln nv by nc. Okay, so if you see here, efi is what? 2 times of efi 2 times of efi minus, this is what? ev. So efi ev. Okay, so efi, this is okay. ec plus ev negative, just we have taken this minus sign common, so inside ec plus ev is equal to what? Take this kt this side, we will get kt ln and Vy and C. Okay, so now see here, just take this two. Okay, take this to this side, take this two common, so we will get from here what we will get? 2 EFI. 2 EFI is equal to, take this side, take this EC plus EV this side, what we will get? EC plus EV. EC plus EV, okay, plus KT ln NV by NC. Okay, so now see here, EFI is equal to what? EC plus EV. EC plus EV by 2. Yes, EC plus EV by 2 plus KT by 2. KT by 2 ln NV by NC. Okay, now this is my Fermi energy level. Okay, so now if you see this EC plus EV by 2 is what? This is nothing but E mid. Okay, mid gap energy band. This is what? Mid energy gap. Yes, mid energy gap means it is the center. It is the center of forbidden energy band gap. Yes, so this is nothing but EFI is equal to what? We can write this EC plus EV by 2 as E mid. E mid, yes, E mid gap. You can write E mid gap. This, okay, E mid gap. So plus KT by 2 plus KT by 2 ln NC NV by NC. Yes, NV by NC. This is actually what? This is actually our position of intrinsic Fermi energy level. Okay, so this is the position of intrinsic Fermi energy level. Okay, position of intrinsic Fermi energy level. This is my E mid gap, which is nothing but EC plus EV. Means it is the center of what? It is the center of forbidden energy band gap. Yes, center of forbidden energy band gap. So now let us proceed further. So we will again simplify it in. So we will simplify it further. Okay, we will see what type of result we will get for this position of Fermi energy level with respect to this NC and NV. Okay, so now see here. So just note down this. Okay, so then after that we will see further. So let us see here. So then this what we got here, EC, this EFI, okay, EFI is equal to E mid gap plus KT by 2 plus KT by 2, okay, plus KT by 2, then ln NV by NC. Yes, now see, let us take this E mid gap this side. What we will get? EFI minus E mid. EFI minus E mid gap. EFI minus E mid gap is equal to KT by 2 ln NV by NC. Okay, so this is my difference between center of forbidden energy band gap and intrinsic Fermi energy level. Okay, so this is the position of intrinsic Fermi energy level. Okay, this is what difference between intrinsic Fermi energy level and center of the forbidden energy band gap, which is equal to KT ln into KT ln NV by NC. Now see here, as we have seen that here, let us see here, as we have seen that NV is equal to what? NV is equal to 2 into 2 pi MP star KT divided by h square to the power 3 by 2. Yes, this is what NC is equal to 2 into 2 pi MN star KT divided by h square to the power 3 by 2. Yes, to the power 3 by 2. Now see here, to the power 3 by 2. Now what we can see here, what we can see here, this NV and NC both are proportional to effective mass. Yes, both are proportional to effective mass of electron and effective mass of hole. Effective mass of hole. Yes, when we put this value here, what we will get? All factor, see here, n v is equal to 2 into 2 pi kt h square. This is same. Let us, this is equal in both case. So let us put it as k dash into what? mp, k dash into mp star to the power 3 by 2, and this is what? nc is equal to 2 into k dash mn star to the power 3 by 2. Yes, to the power 3 by 2. Just put this value here. What we will get here? EFI minus E mid, EFI minus E mid gap, E mid gap. Okay, so this is EFI minus E mid gap. Yes, EFI minus E mid gap. Just write it as somewhat bigger. Okay, so this is what? EFI minus E mid gap is equal to what? kt by 2 ln nv is what? k dash mp star, k dash mp star divided by k dash mn star to the power 3 by 2. Yes, k dash get cancelled, and we will get EFI minus E mid gap is equal to kt by 2 ln mp star divided by mn star to the power 3 by 2. Yes, so now see here, EFI minus E mid gap is equal to 3 by 2. That is, let us take this side, ln x to the power n is what? N ln x. Okay, so let us take this power this side. So we will get what? 3 by 4 kt ln mp star divided by mn star. Okay, so now this is our final position of Fermi energy level. Okay, so which depends on effective mass. Yes, because the density of state, function in conduction band and valence band, these are depending on what? Effective mass of electron and hole. Okay, so now we will make the conclusion here that if see here, first case what? If mp star, effective mass of hole is what? Effective mass of hole is equal to effective mass of electron, which implies that what? Which implies that EFI minus E mid gap is equal to what? 3 by 4 kt ln 3 by 4 kt ln, both are equal means it is what? 1. Yes, ln 1, which is 0. So therefore here EFI minus E mid gap is equal to what? 0, which implies that Fermi energy level EFI is equal to what? Is equal to E mid gap. Yes, E mid gap. So we can see that Fermi energy level EFI is equal to E mid gap is what? EC plus EV by 2. Yes, EV by 2. This is when effective mass of electron is equal to effective mass of hole. Yes, so when effective mass of electron and hole are equal, then position of Fermi energy level is exactly at the center of forbidden energy band gap. Yes, forbidden energy band gap. That is when effective mass of electron and hole are equal. Okay, when effective mass of electron and hole are equal, then that time the intrinsic Fermi energy level. Okay, that time the position of intrinsic Fermi energy level exactly lies at the center of forbidden energy band gap. Forbidden energy band gap. Okay. So now see for case second. Let us see the case second. Case second. Second is what? When if MP star, if MP star is what? If MP star is less than Mn star, if MP star is less than MP star is less than Mn star, if MP star is less than Mn star, then that time this value will come negative. Okay, this value will come less than 0, less than 0. Okay, so less than 0 when MP star is less than Mn star. Okay, so which implies kt ln MP star divided by Mn star. Mn star is less than 0. Yes, less than 0, which implies that less than 0, which implies that EFI minus E mid, EFI minus E mid, EFI minus E mid gap is less than 0, which further implies that EFI Fermi intrinsic Fermi energy level is less than E mid gap. Yes, E mid gap, which further implies that EFI is less than EC plus EV by 2. Yes, EFI means Fermi energy level. Position of Fermi energy level is less than EC plus EV by 2 for what? For Mn star greater than MP star, means MP star is less than Mn star. Okay, or otherwise you can say MP star is less than Mn star. Okay, when MP star is less than Mn star, that time the Fermi intrinsic Fermi energy level. This is my energy band gap. Yes, energy band gap. This is my center. Okay, this is my center. Center means what? This E mid gap. EC plus EV by 2. Yes, this is my mid gap. Now this time EFI will lie somewhere here. Okay, somewhere here. This is my EFI. Okay, EFI for what? For Mn, for MP star less than Mn star. Okay, so when MP star is effective mass of hole is less than effective mass of electron, that time Fermi energy level just lies below the center of forbidden energy band gap. Okay, below the center of forbidden energy band gap. So now third is case third. So let us say case third. Case third is what? Case third is when if effective mass of hole, if effective mass of hole is greater than effective mass of electron, then which implies that kt by 2 ln MP star divided by Mn star is what? Greater than 0. This is greater than 0, which implies that what? Which implies that EFI minus E mid gap, which implies that EFI minus E mid gap is greater than 0. Okay, which implies that EFI is what? EFI is greater than E mid gap. Yes, E mid gap. Okay, so which further implies that EFI is greater than EC plus EV by 2. Okay, so that is for what? That is when MP star is greater than Mn star. Yes, MP star is greater than Mn star. These are the three conditions. Okay, these are the three conditions for the position of intrinsic Fermi level. Okay, intrinsic Fermi level when it lies at the center, when both effective mass of electron and hole are equal, when it lies below the center of forbidden energy band gap, when effective mass of hole is less than effective mass of electron, when it lies just above the center of forbidden energy band gap, when effective mass of hole is greater than effective mass of electron. These are the three conditions under which we can decide the position of what? We can decide the position of intrinsic Fermi energy level. Okay, intrinsic Fermi level in where in intrinsic semiconductor material. Okay, intrinsic semiconductor material. And what final conclusion is, what final conclusion that we will see here, the final conclusion. Okay, so this is all these 3 points. Okay, you can note down that. Okay, everything. So let us see now final conclusion for this intrinsic Fermi energy level, so that we have derived. So final conclusion is that the effective what the Fermi energy level must move away. Yes, that is what final conclusion. Final conclusion. Final conclusion. Final conclusion for intrinsic Fermi energy level. Intrinsic Fermi energy level EFI. Final conclusion for EFI is that intrinsic Fermi energy level EFI must what EFI must move away. EFI must move away from what? Away from EFI must move away from intrinsic. Okay, away from band gap. Okay, away from energy band gap. Energy band gap. Yes. So forbidden energy band gap. So that is what intrinsic Fermi energy level that must move away from energy band gap. Okay, with large density of large density with large density of state function in order to what? In order to maintain the equal number of electron and hole. Okay, so equal number of electron and hole in conduction band and valence band. Yes, so that is what the final conclusion that we have about for intrinsic Fermi energy level. That is intrinsic Fermi energy level that must move away from what? Away from energy band gap with large density of state function in order to maintain the equal number of electron and hole in the conduction band and valence band. Okay, so that we can say that it is a intrinsic semiconductor material where the concentration of both electron and hole are equal. So therefore we can call this both concentration as intrinsic carrier concentration of electron and intrinsic carrier concentration of a hole. So this is all about intrinsic Fermi energy level, or we can say position of intrinsic Fermi level. Okay, so how it varies with respect to effective mass of electron and hole that we have seen, and we also have seen what the final conclusion about this. So always the Fermi energy level, intrinsic Fermi energy level that must be move away from what? Move away from the energy band gap. Okay, in order to maintain the equal number of electron and hole concentration within the semiconductor material, within the intrinsic semiconductor material. Okay, so that's all for today. Okay, so thank you very much. Okay.